So in this question, we have three graphs. And what we might notice about the first one is it's an xt graph. The next one is a vt graph, and this one's an at graph. So we might suspect these are about the same phenomenon. Let's do an RGA of this one. We can read position time. The slope is delta x over delta t, which is the velocity. And the area, xt meter seconds, has no value. So what we can see from the slope is the slope is changing, so the velocity is changing. It's large and it's negative, and it becomes 0, v equals 0, and then it reverses direction. So it's headed in a negative direction. This is positive, this is negative. It's headed in a negative direction. It's going very, very fast, like this. Comes to a stop, it reverses direction and heads in the positive direction. Now, of course, we know there's acceleration also because it's curved. But that's a picture of what's going on from that detail. The next graph, we have RGA. So the velocity and time are things we would read. The slope is delta v over delta t, which is the acceleration. And the area is v delta t, which is the displacement. Now, what this says is the velocity starts out negative, which is what we said up here. It decreases to 0, which is what we said right there. And then it increases in the other direction. So this supports exactly what we found from the xt graph. These two graphs are showing exactly the same motion. The slope is the acceleration. The slope is constant. It's a straight line. And it's positive. We look at our acceleration time graph, and sure enough, if that's 0, this is a positive value, and it stays the same. We can read acceleration time. The gradient is delta A over delta t, which is the rate of change in acceleration, which has the name jerk. And the area is delta A times delta t, which is going to give us the change in velocity. All right, so for a marble moving in one dimension, which could describe the motion of the marble? Rolling along a floor and then bouncing off the wall. Well, that would be constant velocity and then immediately reversing direction without speeding up or slowing down. It would have a constant velocity, then it would have a minus constant velocity in the other direction. It doesn't say there's ever a 0 velocity. So this can't be right because our graphs show a 0 velocity. Rolling down one side of a bowl and then rolling up the other side. So if we had a bowl, let's say this is the positive direction and this is the negative direction. So we start out at a position of 0. Let's say that's 0, and the negative direction is in that direction. This shows it going very fast to start. So notice when we release this marble, it'll be slow, and then it will get faster. What we see happening in our graph is it starts out the fastest at the beginning. This is something that's going to accelerate, right, from slow to fast, but this says it's going from fast to slow. So it can't be that. Now, intuitively, that might feel right because there feels like a back and forthiness to what's going on in this phenomenon, but it doesn't match something rolling back and forth with a ball. Rolling up a ramp and then rolling back down. Well, let's see. If we're going to roll a ball up the ramp, we've got a large velocity. It's fast, and then it's going to slow, and then it's going to reach 0, and then it's going to reverse direction and come back down. And if we said this is the positive direction, if we said this is the negative direction and this is the positive direction, then it would have a big negative velocity, and then it would go to 0, and it would reverse and come back positive, which is what we see here. And in that scenario, it's getting slower on the way up and getting faster